Good morning. Thank you very much for inviting me. Pleased to be here. We come over from Boston, and on the way here, looked at a lot of what's going on around the world in storage. And I remember when I got started in storage, it was like around 1993. And I was down to family, friends, and pets who wanted to talk about storage because it was too expensive. And now we've got very vibrant groups across the world in storage. I was just in Tunisia with about 60 countries, and everybody's talking about storage and renewables. And so one of the things that I've kind of the path that we've taken at Acelerex is I got into battery manufacturing and kind of a failed venture back in 2016 where we made a factory, raised like 400 million US dollars, started making batteries, and we failed. We failed miserably at it. But the analytics, the controls, all these kind of things were very vibrant. And so I started the Acelerex company. And since then, I've been able to attract some very interesting people to the company. I've got the former CEO of GE Power and Water. He had 52,000 employees, $32 billion a year. He's on the board, and as well, the former CEO of PGM, the largest interconnected power grid in the world for market. And he started the first battery market, Terry Boston, and he's on our board as well. And I'll kick off from there. So a little bit of history. So one of the things that the renewables industry has done really well at is a big PR campaign, right? It's similar to nuclear. When the British introduced nuclear, they said it was going to be too cheap to meter, and the public dug that. They liked that. And so what the renewable people have done is they've taken solar and net load, and they've called that the duck curve. In most societies, the duck is one of the most beautiful animals there is. And so we like the duck. We like its beauty. We like its feathers. We like its colors. It's been an amazing PR campaign because the actual solar power isn't that great from an operational point of view. It's very difficult to control, and more solar that comes in, the more and more operational problems that show up. And what we're finding around the world right now is that everybody can do energy policy. It's not hard. You take your load, multiply it by your percentage, set your decarbonization code goals, and declare victory. And then what happens is as you're on that path to victory, as countries are on that path to victory, they start getting the operational issues with the renewables. So what you'll get from my talk is a little bit more pragmatic view. I've set up Acelerex 7 years ago. It's fully profitable company. It's a startup. It's a successful company. But I had to take a path of what is pragmatic. I couldn't believe everything people were telling me. How many battery companies are going to go bankrupt in the next 2 years? Do we have a number? How many battery companies? Maybe a number of them. How many actual battery companies have actually been commercialized? How many battery technologies have been commercialized? If you look at the academic journals, you'll think that there's all kinds of battery technologies out there. There's very few actually that have been successfully commercialized. How much money does it take to commercialize a battery? I would argue it's infinite. It's an infinite amount of money to commercialize a battery. Doing small battery projects, that's one thing. Doing batteries at scale, like lithium ion, that's a whole nother ballgame. So what we're going to start with is a little bit of intermittency and dependency of weather conditions, challenging transient stability electricity supply. I work with a lot of islands. Renewable power on solar, you can lose 80% of it in less than a half a second. So a cloud flies over, 80% of the power loses in a half a second. Now that's a real fast duck. Usually ducks don't even fly that fast. But so it's a great PR campaign, but it has operational problems. So one of the things that we're finding in a number of countries is the transient stability becomes very important going forward for grid. Because if you can lose 80% of your production in less than a half a second, which technologies can handle responding to that? A lot of the thermal technologies can't handle it. It just physically can't handle it. It comes down to batteries that need it. And that's why you see the big battery push. Another one is the grid stability, like I mentioned, the sudden loss of renewables requiring reserves, overflowing distribution feeders. Anybody hear about overflowing? First, when solar was starting to get into the distribution feeders, the engineers, protection engineers, got worried about, oh, there could be reverse power. That is, there's more power generated then the load is coming into the distribution feeder and you could have reverse power. Well, there are some countries that have gone past reverse power and now are at the conductor limits of the distribution system. And so they're stopping the connection of solar because there's too much on particular feeders and it's causing reverse power beyond the actual circuit capability and the stability levels of the country. These kind of phenomena are showing up in like mostly island grids. A couple of interesting storage needs, balancing supply and demand. One of the things that the whole world has spent its time on is supply. So we're all talking about supply, and we're just so happy to talk about resource change and supply change. But something happened in the last 2 months in the United States. Everybody kind of woke up. The New York Times, the Washington Post, the Wall Street Journal all said, we've got a problem. Load is growing. It's no longer a resource change problem that we have. It's actually a load growth problem. And the load growth is data centers, like what Europe is wanting to do, reshore manufacturing, unfettered immigration, and bringing chips from Taiwan back into the United States. So what we're doing is at the same time, we're playing this very dangerous game of chicken in the Western world right now. On one hand, we've labeled all fossil fuel as bad. And so we want all baseload technology out of the way. And then on the other hand, our baseload electricity requirements are increasing. So right now, a big gap in policy making is baseload. Baseload is not coal necessarily. It's not natural gas. It's a technology, but it's a load requirement. So what the US has successfully done in the last 2 months is move the discussion from resource change to serve load. That's why we have these resources, and to serve load. And so it's a very interesting point right now, because at the very same points that we're trying to retire the fossil fuels, we're actually going to see load growth. The US sat pretty much flat load growth for the last 10 years, and now it's projected to rise, like about 38,000 megawatts over the next 5 years. Texas alone came out with the load forecast in 2 to 5 years, going from 70,000 megawatts to 150,000 megawatts. That's perfectly normal to see a load go in 2 years, double the load. That's not really that normal. And it's partly because of the data centers, the manufacturing, bringing clean energy back, and immigration is causing this increase of load that we'll have to deal with. A couple examples: Hawaii adopted a capacity-based renewable dispatch generation contracting mechanism. So one of the problems that we've had is solar kind of led the way. And then in the United States, we got kind of conjoined twins. Solar's returns were coming down because of the Chinese. So they were rationalizing and commoditizing it and subsidizing it. And so the returns on solar was coming down. So the solar community in the United States decided, let's reach over here to the storage and hook it to solar. So storage was only good in the United States if it was connected to a renewable. Now, if you do a lot of grid study, you find very quickly that that's just not the case. There's all kinds of applications of storage that can help renewables, but it doesn't have to be inextricably linked like a conjoined twin to renewables. It can actually help with clean peak. It can help with a number of policies. So we were successful in the last couple of years to get the Inflation Recovery Act in, and we cut the relationship between storage and renewables. Storage still provides a lot for renewables, but it can also do a bunch of other things too for the grid that's beyond what the renewables can do. So, and then we did the Inflation Recovery Act, which is the largest energy act of mankind. There's nothing on the order of it. It's probably one of the largest protection mechanisms that you'll ever see on Earth. I'm surprised I don't see a bunch of lawsuits, but instead I see a lot of bureaucrats making the same laws. They actually like it. So Canada liked what the US did. Europe is kind of on that path with the Net Zero Industrial Act and the the Renewable Energy Directive. And so the Renewable Energy Directive, that looks really successful, up to 900 gigawatts, 975 gigawatts on the way to 1,000 gigawatts. So that's looking really good. The question that I have is, will the net zero industrial act, will that bring manufacturing? Because you just had one of your most charming in Europe battery startups, Freyr. They're going to Georgia and they're setting up their factory in Georgia. They're not setting it up in Norway. So they're you're seeing, because of energy costs, because of the incentives, the tax incentives, you're seeing movement to the United States of manufacturers, Chinese, a number of entities. And then Burkina Faso. So one of the things that was the challenge is hooking solar, wind, and then how to bring in the business model of storage. So that was one of the challenging parts in it. Initially, it was concessionary. So you'd see a solar project and you'd see like a 20 megawatt solar project and 2 megawatts of storage. It was kind of concessionary, and it was bundled in with the PPA energy term, like a fixed in-feed tariff. And it was kind of bundled in, and it was kind of like concessionary, just to make policymakers happy that there was some storage movement. And now it's moved a little bit beyond that in a good way. And so I'll get into that a little bit. So one of the issues as to why policy gets difficult. So when you first do it, like I said, setting up energy policy, you can take any graduate from any leading university in any policy program, and they can multiply a couple numbers, multiply percentage times load, and then call that how much renewables you need by energy. But then when it says keep it reliable and keep it resilient, that's when they start scratching their heads and they have to do something they don't necessarily want to do. They got to bring the engineer to the table. Because you can do policy, you can do percentages, but when you need reliability and resiliency, you got to live with the engineers. You got to bring the engineers to the table. It can't just be the policymakers, because they can't see it all the way through. So one of them is the when, or the what, the why, the where, the when, and the how much. So right now, each country in Europe, what, why, when, where, and how much storage. Do we have that laid out? We don't have it laid out. There's at least 70 countries on Earth that have no clue how much storage they're going to need going forward. They have ideas, but those 5 questions are the toughest questions right now to to augment a renewables policy. The other one, so that's what we call least cost capacity expansion planning. Then we have the production cost, as there's still fossil fuels in the system. So there's still efficiencies and optimizations that need to take place. We've gone down the path of what's called a stack services emulator to maximize profits and savings and to dispatch the storage, because all our old textbooks that we like, now I've been at it for 25 years, so I'm a young man, I'm just starting. And my textbooks that are on my shelf are from the 1970s, and they love to talk about co-optimization of energy and ancillary services. That's the going technology. And if you come out of a university with co-optimization of energy and ancillary services, most competitive markets are operate that way, many of them around the world. Is that still necessary? Is co-optimization of energy and ancillary, is that going to be a sufficient technology, a sufficient foundation when you have marginal costs as the marginal cost of the electricity supply in some areas could go down to almost zero or even negative in some cases? So one of the questions becomes, what about peak shaving? What about shifting the renewables? What about other reasons for co-optimization? Right now, the whole world has its brain around co-optimization of energy and ancillary services in markets. But what you're going to find is storage, as you look at many of the publications, can have unlimited services. You can think of all kinds of virtualization of the storage, where you can virtualize the megawatts and the megawatt hours of storage. So our old methods, and I call them old now, is co-optimization of energy and ancillary service, because it's going to go way beyond that. If you want resiliency services, reliability services, what is the future Marginal cost of the next megawatt of capacity put on a grid. What is that? Is that the capital cost of storage? Is that the next marginal megawatt? Do we go to a grid that starts with flexibility and ends with capacity? That we need grids that have capacity and flexibility. So some of that kind of thinking. So we built methods and optimizations that go beyond the co-optimization of energy and ancillary service. The other one that's very important is power flow. We're very used to, in the world of electrical engineers, we're very used to looking at the worst case, the most severe condition, so the highest load case, and then we take a snapshot and we only run 1 hour and we declare victory. We say, wow, we've done something amazing here. We got a 4-quadrant power flow, and we've been able to solve this problem. We see the future, I've seen the future as it's actually a time series power flow that's coming. Is you're going to need time series like on the distribution feeders. And that's like, wait a second, nobody has really time series. But if you want to look at some of the operational issues, it's actually at the minimum loads with renewables coming in at the minimum loads. And that's a time series kind of phenomena of how it works. Likewise, transient stability, I mentioned that, and then forecasting. There's a lot of forecasting because all the countries right now across the world are talking about trillions of dollars of investment. If you add it up, it's a boondoggle of the biggest boondoggle ever known to mankind, this clean energy investing. So we got into valuing the plants. How do you value all these plants? Because there's going to be a ton of investment, plant after plant after plant. There's the grid to hold it together, but then there's the individual investments. A couple of them is the typical integrated resource planning framework that's used pretty regularly around the world. A least cost capacity expansion of production costs and valuation techniques. And then there's a number of methods. We've recently applied this in Bangladesh. A project that I've participated in for about 9 months was a project with the World Bank where the idea is to do hybrid solar and storage PPAs. And you would think, oh, we should have had that worked out years ago. It's just starting to get worked out. We're just barely scratching the surface of hybrid PPAs, power purchase agreements. And there's a lot of interesting terms that need to come into PPAs for renewable and then for storage. So the World Bank, we helped them define this. There's a report link in there. And so we broke it down to a 4-phase process, overall system planning. That's the what, the why, the where, the when, and the how much. You still need that because at the end of the day, we're not building these renewables because we've fallen in love with them. We're building these renewables because we have to supply load. And we've decided as societies to switch from one field type to another field type. But at the end of the day, this is for building load. I mean, this is for supplying load ultimately. So you got to use a system needs analysis to get to the requirements of how much of different technologies are needed. Phase 2 is define the project, assess the project requirements. Phase 3 is consider the business model options, assess the advantages and disadvantages of the business models. And then phase 4 is determine the most suitable business model based on the decision tree. Now, as I mentioned earlier, the lexicon of policymaking, base load has left that. If you look at most policymakers, have them stand up publicly and say, base load, you don't see a whole lot of that across the world. You hear wind, renewables, and storage. So how then do we synthesize, and hydrogen, of course, how then do we synthesize base load to supply base load? Because most grids have a 50% load factor, at least a 40% load factor. That is the max load. The min load is 40%, 50% of the max load, the peak load of the system. That means there's a base load that needs to be 24/7 running power. So how do you make that with renewables, right? Because you've got intermittency on solar, you've got intermittency on wind, and then you've got the only thing that mankind can control is the storage to be able to try to control the weather and how it produces electricity via combining a net renewable plus storage. So a couple examples. We recently did the Mauritania solar plus storage project. We also did a wind project there. And that was to look at the demands and needs assessment. We did a least cost capacity planning. We looked at the grid flexibility, and we did high level locational studies. What we are finding is that we're very, very smart. Humans are super smart right now with technology, with information. In a way, we're maybe a little too smart, because in a way we confuse people, because we go and we say, hey, this storage could do 25 services. In reality, maybe 3 of them are really can get into a grid code, can actually get into an operational system, can actually be utilized. I've been to a few countries where you got diesel, solar, and battery. I go look at the diesel. Okay, I get what that's doing. I go look at the solar. I get what that's doing. What's your battery doing? Sometimes we turn it off because it's too complex. It's too cool. We'd rather just start our diesel engines when the solar's not there. When the solar's there, we'd rather just turn off our diesel, and that's where our savings is at. And so I've come across a couple batteries that are sitting there, not really being utilized. So I have a rule of 3 plus 2. So most batteries, you need to find 3 power services and 2 volt VAR services. So 3 plus 2. If you have batteries that are in the 3 plus 2 category, you're probably going to find a business model for them. If they're in the 1 plus 0 category, there's 1 power service and no volt VAR services. There's very few of those batteries that are profitable now. Maybe on a transmission line deferral, and we've seen a couple of those. Nantucket has one of those. There's a couple of those kind of situations, but we found over the years that single service batteries, frequency response markets are shallow, so single service batteries have less of a business model nowadays than, say, 3 power services and 2 volt VAR services. Another one I've been working on is Barbados. Barbados has the most aggressive clean energy goals on the planet. It has decarbonization by 2030. The Prime Minister ran on that successfully and has done a lot of the work to get that in place. And we've been helping them with a storage framework, integrated resource plan. We've helped out with the policy. We've helped with the cabinet papers, come up with their PPAs. We've actually derived an energy storage tariff, a very nice tariff on how to do the energy storage, like through capacity payments. Now, we've done energy storage. I've personally been involved in energy storage roadmaps, probably about 30 or 40 of them globally. And what I've come to is there's about 50 different policies right now around storage. They fit into all kinds of categories, from cleaning peak power up to making baseload power to economic stimulus, all kinds of categories of where the policies are fitting in. And what policies are for California might not work for the UK. And so when we did the state of charge study, which is a pretty famous study, I used a 5,000 node supercomputer, ran a bunch of cases of the state of Massachusetts, and came up with 12,000 megawatts of storage. And at that time, the DOER, the commissioner, said, that's a lot. We can't handle that. We can't do that. Our institutions can't handle that. And so we're going to drop that back to 600 megawatt hours. And so they went in and they put in the 600 megawatt hours, and that's been done now successfully. But you can look it up. It's the state of charge study for Massachusetts. It was done by Judith Judson, the former commissioner of DOER of Massachusetts. Like I said, at the time, I had put together a 5,000 node supercomputer. It's just right ahead of when the cloud has really gotten better than having a computer, an actual standalone computer. And we ran thousands and thousands of cases of the state and said, hey, if you want a total clean energy policy, you're constricted on natural gas, you want all this offshore wind, you need a lot of storage. And so that's kind of that piece. Now, hybrid PPA, this is what came out of the World Bank work. And so you have, originally you had separate payments. So the way that solar works right now is just $1 per megawatt hour, $1 per kilowatt hour. So that's the going business model for solar. Concessionary storage, when we talked about, we're moving on from concessionary now to actual storage financing. And concessionary storage was just tack the storage in on the $1 per megawatt hour and just uplift the $1 per megawatt hour, some sort of amount, and pay off the storage. What's the problem with that? The problem with that is you have no dispatchability. What's the incentive for the off-taker to give you any dispatchability with that kind of contract? So that's got a fundamental problem if it's a single term PPA and you try to bundle the storage in, because what's the dispatchability? How do you get the controllability? How do you get the grid services out of it? What's the incentive for the developer to do that? That kind of thing. Then we introduced this. This is what I had been pushing for a number of years, is the dollar per megawatt hour and a capacity contract for the storage. So do an energy contract for the solar and a capacity contract for the storage. So you pay the storage in $1 per kW month. So you get a monthly payment, and then you just have to meet a used and useful criteria. Used and useful is standard regulatory parlance, and used and useful means what is the storage doing something each month, daily? Is it available? Is it doing a number of services? That kind of thing. So that's the capacity, and then you can have just a single capacity contract for standalone storage. What's the idea of the capacity contract? The idea of the capacity contract is, for the most part, the storage is used for maximizing social welfare, right? Because the storage is only there because you have to have it there, not because you want it there, not because it's the most exciting thing we've ever done, not because it creates business and economic opportunity. That's not why storage is there. Storage is there because you have to have it. It's like bringing the cats to the water, and the cats are the renewable folks and the policymakers around renewable, and you have to bring them to the water in the sense of storage as the penetration levels go up of the renewables. So then you could have standalone storage. You can have, it has low firm power, high dispatchability control, and with buyer bears more risks. And then with a two-part contract, you have low firm power, high dispatchability, and control with the buyer. The buyer bears more risks. Now let's go all the way to the other end of the scale here, 24/7. Anybody hear of 24/7 solar plus storage contracts? How many of those have been signed in Europe? None? One? None. The only ones who are doing it are the Indians right now. The Indians are doing 24/7. Guess what you have to pay, what the penalty price is if you don't show up with the energy on a 24/7 contract in India. It's right now 4 times what you would get paid. And you'd say, wow, that's painful. I get 4 times damages for what I'd normally get paid $1. I get $4 of damages. In most markets, it's the cost of replacement. So the cost of replacement is the penalty in the contract. That is, if you don't show up with the power, there's not a lot of nice people in business. You need to show up with the money. And there's a cost of replacement. In India, the argument goes very simply. Where are you going to get the power to replace the power? That population is growing. That energy consumption is growing. So there is no replacement power. You got to, so they really want delivery. And so they're coming to the 24/7 contracts, the first in the world that I've come across. And these are single payment, 24/7. And so what happens is you guarantee a profile coming out of the solar plus storage, the wind plus solar plus storage, and you guarantee a power profile. Are there some risks in there? Is there some deliverability risk that, hey, what if there's 2 or 3 days of low solar production? So there could be some risks there. And then we have 24/7. And then time variant rates are the other one. So those are about the 5 contracts that you can see across the world right now, where the direction. Another one is the tariff and PPA terms. So here's some of the services: the frequency response, the spinning reserve, the voltage control, the power factor control, renewable energy firming, renewable energy ramping, renewable curtailment reduction, distribution hosting capacity, and peak shaving with renewables. And we did a tariff, and here's like a capacity value. This was in Barbados dollars, 47.8 kilowatt month for the storage, and before IRR 10-year 7%, before MPV. So we did that. And then here's one, Mauritania, where we're showing that we're taking the off-peak generation and we're showing to supply peak load, because in Mauritania it was about supplying peak load. So using the storage, the main service, was to really go after and supply the peak load. Not everybody, that's the issue. Not everybody has the peak load is the key issue. It's an important issue for a lot of folks. The other thing to introduce with storage is autonomous services. Voltage and frequency can be controlled autonomously. The idea that you need central dispatch layers for everything, that's important at the sub-transmission, at the control center, at the distribution center, and at the DER sites. So we've introduced concepts of autonomous services with storage, things that you can measure locally. You can already get 3-4 storage services without central dispatch. So you can measure voltage, you can measure power, you can measure frequency, and there's already 3-4 services there that you don't need centralized dispatch. Why are we kind of pushing back on centralized dispatch? Because it slows the system down. If you, the system of renewables adoption, that kind of thing. Okay, so energy storage policy roadmap. I've looked at a lot of the roadmaps. I've helped participate, make a lot of roadmaps, and here are the key elements. You need a policy piece, because most, like what I said, is most of the renewable policies around the world are worked out for the most part in percentages. But they don't know what to do with the storage. They don't know the purpose of the storage. They don't really have a reliability policy. So you say we've got a decarbonization policy, but what about reliability and resiliency? We still got to supply load. So a lot of times in the policies, you don't see that piece in there. That piece comes in with the storage. Then ownership structures, guidelines, how that can all work. Like if you want to deregulate the generation, that kind of thing. Then regulatory, integrated resource planning, PPA rates, updates to legacy structures. Should you do a FIT for storage? Does a FIT for solar, a feed-in tariff, and a FIT for storage, are they one and the same? They're not, because a storage doesn't have a widget. It's not like a 1 kilowatt hour comes out and that's a widget. The storage has services. In fact, the storage doing nothing has value. If it has a state of charge and it could be released into a load at a certain time, that has a value, yet it's not doing any work. It's just sitting there idle. And then the grid codes. Another one is the storage licenses, treating of storage, process with technical and financial requirements, monitoring requirements, terms and conditions. Like one of the countries I'm coming up with, their licensing. What do you get? What do they charge to license a storage? And I've come up with, it's about 25% more effort to license a storage system than to license a solar system, if you run through all the work that requires. Then the grid codes. A lot of the grid codes aren't ready for storage. They're not specified for storage. Things, very simple things. How do you calculate cycles? How do you calculate efficiency in the grid codes? Let's say it's for social good and you have dispatchability. Who pays for the losses, the developer or the system? And how do you calculate those losses? Because those losses over time are quite important to account for. Is it a credit system on meters, differences between purchases and sales? And then PPAs, I just went through that in pretty good detail. To get storage into roadmaps and to get it into policy, I broke it down into 3 phases based on all the work I'm doing around the world. The first one is the what, why, where, when, and how much. The second one is propose reforms and accommodate the storage. So first you have to analyze all the policy that exists and say, where do you puncture in the storage policy? Where does that need to be put in, and how does it, where in the grid code? What kind of transient stability is important for reliability? What is the regulatory approach? What are the key PPA kind of terms that would need to come into play? And then the third phase is doing the projects, getting projects once the policies are set up and the regulatory is set up. Now, a lot of times this feels like a very long process. It takes forever. We've seen it done in about 6 to 12 months. It usually takes 2 to 3 years ultimately to really work in a true storage framework, a true storage in a sizable country with a sizable load, even smaller loads, say 200 megawatts, 400 megawatts. You could be 2 to 3 years out once you start talking storage and getting that through the regulatory, the grid code, the policy, all the different pieces to licensing, those kind of pieces. Now, I want to get to the duck curve, because one of the things that I looked on the duck curve is this guy. Rarely do you see the solar folks make this curve. It looks like kind of like a transistor curve, right? What I did is we like to make duration curves in power. So you take your highest power and you have a duration curve, and then you come down to how much percent time are you at your highest power, how much percent time are at your lowest power. Well, I did that for solar. And if you look at solar, There's a lot of days, these are days of year. There's a lot of days with 30% for this particular projects, a lot of days with 30% capacity factor. But once you get up to days over about 300 days of the year, you're between 60 days of very low power factor coming out of the solar. Those days are serially correlated, usually through storms, through dust events, through different things. And normally you have one bad solar day follows the previous bad solar day because production day. And so I've made it as a cross, because after that point, you've got storage or you've got prayer. You've got to do something to take care of that, because that's where long duration storage comes into play. A lot of times people, oh, we got to do long duration because it's cool and all that, but it's really for that. That's the main reason, because you drop off your production. You'll see a very similar kind of relationship in wind, not as strong. And so what we find is just ramping controls are very useful. Here's the duck curve for a country, the Barbados duck curve that we've made. It shows the ramping, it shows the low solar, it shows the negative, the oversupply. And so that's been coined the duck. And that's the worst power curve you could ever have. But we painted it and we feathered it beautiful, but it's hard to work with as it gets, as net load of load minus renewables diminishes the load. That's a very difficult curve to control. We're seeing it with California right now, of all the work that's going on in California to be able to control that in a big way. Now, is it only the duck curve? Does anybody else have any kind of curves? I was just on with the Chilean system operator, and they have the penguin curve. So their most beautiful mammal or bird is a penguin. And so they call it the penguin curve. And then I said, what about the baby penguins? So we can have a big, beautiful family, adult penguins and baby penguins. And what are the baby penguins? Oh, that'll happen in Santiago on all your distribution feeders. Do you have a renewable energy program? Do you have a DER program? Oh, yeah, we got about 7 gigawatts that we want to spread across the rooftops of Santiago. Okay, that means you're going to have a bunch of baby penguins. Every single distribution feeder is going to get a penguin, just like a duck curve. So these things are going to multiply as the distributed energy resource programs come into play. Another one was Bangladesh. Bangladesh pays a lot of money in diesel fuel. So we ran a study, a big study. European Union ran a study, some other people ran studies, and we implemented like pilot projects, how to do that, introduction of autonomous grid services because they don't have much of a dispatch system, introduction of energy storage tariff, standardization of power purchase agreements, policies to encourage IPPs, grid code, update with energy storage technologies, and action plan for DERs. What we found in Bangladesh was this is where the time series power flows come in. So this is like the time of day here, and this is multiple days. And depending on the penetration of the solar, this is the voltage disturbances, and this is past the red line is past the 5%, typically designed to plus minus 5%. So that's why we're going to time series at our firm. We're going to time series power flows on the distribution systems. Quick rundown of the federal orders in the US. So it's a clean set of, not just because I'm US, I come from the US, it's just a very orderly set of regulatory orders that are very clear. So 745 proved that storage could outperform thermal and hydro in frequency control. So that was established. And that was 755. 745 was the demand response. 755, it unequivocally proved that the storage would have better frequency control than thermal, and you could do pay for performance. And Terry Boston on my board, who was former CEO of PGM, he set up the world's first competitive battery market called Reg D in the United States based on that order. Then you have 841, and what 841 is fair play. Storage gets to do capacity, storage gets to do energy, and storage gets to do ancillary services just like thermal. Before it came in, it wasn't fair play. There was discrepancies in the rules, how they were treating. 845 does issues related to DERs. FERC Order 1000 is non-transmission alternatives. FERC Order 2222 is the beautiful thing. It's double dipping. You get paid twice for the same megawatt. We love double dipping in business models. If you can get paid twice for the same thing you do, you'll do that again. That's nice as long as the pay is good. And so what FERC Order 2222 says is you can have behind the meter revenue model and you can have an in front of the meter revenue model with the same KWs. So that's a fascinating order. And then FERC Order 2023 is very interesting because most transmission queues right now, the US market is 1 million megawatt. And right now in the queues, we have 700,000 megawatts of assets. There's no way all that's going to be built. And so we have what's called queue squatting. And so now queue squatting is where they go file for a queue position to get a transmission interconnection, but they never build anything. And so now it's going to first ready, first serve. Rather than first in, first out, the US is going to a first ready, first serve model. A little bit on advanced storage software. There was a lot of discussion yesterday and all that, so I'll just jump over that slide. Simulation studies, that's readable. Kind of already went through those a little bit. And then just a little bit on, just a quick one here on what we're seeing of the EMS and SCADA features, the IoT functions, the EMS, the SCADA needs to get smarter than it was. And then operational applications for storage. We're seeing SCADA, energy management systems, data acquisition systems, power plant controllers as an area where we're entering. And as of today, we're commissioning with our software a 30 megawatt battery in Holtville, California. It's being commissioned right now with our Rex software that we made. And with that, I think that's it. Thank you very much.